This is Statistics 243 at Berkeley for December 1st, 2014. Okay, let's go ahead and get started. Okay, so the plan for today is I'll finish off this hopefully fairly quick example of doing a constrained optimization in R. And recall that last time I mentioned that R doesn't have particularly sophisticated routines for doing convex optimization or constrained optimization. So this, I'll show you this example in R, but if you really wanted to do this for more complicated problems, you would probably want to go use other tools. And then we'll start talking about numerical differentiation and numerical integration, which are Unit 14, and hopefully get a good chunk of the way through that. And then on Wednesday, and then at some point, starting at some point on Wednesday, and then into Friday, we'll talk some about graphics, a little bit of graphics in R, and somewhat more about just sort of general principles of graphics. And it'll be kind of fun because I'll show you some examples of really bad graphics, and it's always fun to make fun of other people, so we'll get to do that, some of that. Okay, so here's this. This is the last little subsection of Unit 13 here. So there's this R function constrained optim. And if we go ahead and just look in R and do help on the function, what we'll see is it says it minimizes a function subject to linear inequality constraints. So this is going to be less general than some of the problems that we saw in the last few days in terms of having nonlinear constraints, but this will handle linear inequality constraints. And it says it uses an adaptive barrier algorithm. So that's basically what we talked about last time, where you include the inequality in the objective function, and then you approximate that non-differentiable function with a differentiable function. And so when they say down here, they say this logarithmic barrier is added to enforce the constraints, then that's exactly what they're saying. They're saying that this implements what we talked about last time. So let's see, and then it just calls optim for a given value of the barrier function, for a given value of that tuning parameter. Okay, and it says here as this tuning parameter mu increases, the augmented objective function becomes closer to the original objective function, but also less smooth near the boundary of the feasible region. So this is all of the same stuff that we were talking about last time. Okay, so here's the function I'm going to go ahead and minimize. I've already entered the code here to plot it. Oops. So this is called the Rosenbrock banana function, sort of, I guess, for obvious reasons. So people will sometimes use this as a test problem, and it has this nice feature that it's definitely nonlinear in terms of the objective function. I don't know if I have anything more to say about it than that. So I've coded up a function that's called fr here that actually evaluates the function for a given input, and that we have two-dimensional input x1 and x2 here. And in this case, I've also coded up a function that evaluates the gradient. So we've analytically figured out what the gradient is, and then implemented a function to evaluate that gradient. So oftentimes when you're doing an optimization, it's nice to pass in the gradient function, the closed form gradient function, if you can derive it relatively easily. Okay, so then if we go back to looking at the help information, it says the feasible region, so these are the feasible region, so the region in which you can be based on the constraints is defined by, and I've sort of written out the math here as u, this is supposed to be u sub I, multiplied by theta minus c sub I is bigger than or equal to 0. So if we actually went in and look at more details at what it's expecting about u sub I and c sub I, so it expects u sub I to be a constraint matrix and c sub I to be a constraint vector. And so in this particular case, what I'm going to do is I'm going to imagine that we are tasked with the problem of finding the minimum within this region here. So I've written it in comments here. x1 is less than 0.9. So here's x1 is less than 0.9. And x2 is less than x1 plus 0.1. So x2 is less than x1 plus 0.1, so down in here. So this defines the feasible region in which the solution, the constrained solution, can lie. And since we have, sort of the pain in doing this is we have to put our constraints into the exact form that R wanted, which was that, sorry to keep switching back and forth here, that R wanted things in this form here. So it wants things in a form where the CIs are on this side, and we have greater than or equal instead of less than or equal to. So we need to do just some simple algebraic manipulations to put things in that form. And so eventually, after doing that little bit of algebra, I think when I first did this, I made enough mistakes to embarrass myself. But this is the UI-CI set. So this is the matrix and the vector UI-CI that corresponds to these two constraints here. The x1 is less than or equal to 0.9, and the x2 is less than or equal to x1 plus 0.1. And if you just work through the basic algebra, you'll see that that does indeed correspond to that set of constraints. But you have to work it out and make sure it's in the form that the function is expecting. Okay, so questions so far? All right, so then if we go ahead and run the constraint optimization, we give it starting values, of course, and we need to make sure that these starting values are in the feasible region. They're in the region that's defined by the constraints and are valid places for a solution to lie. And I give it the actual function, the gradient function, and then the UI and the CI, and I go ahead and let it run. It looks like it went pretty quickly. And then we can look and see what are the values that it found as the optimum. And I have to go back and do the plotting again. Okay, so this is me just saying, okay, this first region that we're going to do it in is here, and it eventually ended up finding that the solution was actually on the boundary here at this point here. So somewhere in here is the overall global optimum, but if we constrain it to be in this region, then it finds that the constrained optimum is on this boundary here. Okay, and I started at, I think, 0.5 and 0, so I started somewhere in here, I guess, is where I started, and then it moved up that way. And I could play around. Here's me just defining a different feasible region. And I went with, when I first did this, just as an illustration, if I forgot to change the initial starting value, well, the region I'm now trying to optimize in, I think, is this region up here, but I kept the same starting value. And so at that point, I realized as soon as I entered this that, oh, it says the initial value is not in the interior of the feasible region. So that's what will happen if you forget to make sure that the starting value is a legitimate starting value. And then if we go ahead and run the optimization for the second region here, so now we're trying to optimize within this set of constraints, well, it finds that the optimum is down here where I put the triangle, where the code plotted the triangle. And I didn't actually quite get this to work. I was trying to do this to actually optimize along a line. And so I tried to be clever and say, well, optimizing along the line x1 minus x2 is equal to 0.1 is the same as putting in this inequality constraint and then sort of the reverse inequality constraint, just flipping the greater than or equal to or less than or equal to. So I was thinking that what I could do was try and figure out what the optimum is if I just restrict myself to being on this line. It didn't quite work because I couldn't quite get it to actually accept a starting value along the line, which I think has to do with the difficulty in actually working with computer numbers not being the exact representation of the number. And therefore, I think because of that inaccuracy, I couldn't actually place the starting value precisely on the line on the computer. So whenever I tried this, it kept complaining about the starting value. Even though obviously 3.1 and 3 is actually a legitimate starting value, and the 3.1 minus 3 is actually equal to 0.1. So at this point, if you were really doing this, you'd probably move to something other than R, but I did use a little bit of a trick here, and I said, well, it's optimizing along that line is almost as if I were to optimize. If I wanted to optimize along that line, it's almost as if I were to optimize in a little rectangle around that line, like this. So I defined I sort of made a fat line in some sense and defined that as my constraint region, and then did the optimization. And I guess I did it with and without including the gradient function. And I think that's because for some reason when I did it with the gradient function, it seemed to converge to a place that was not, obviously not just from the picture, the actual minimum. So I don't know that I've ever figured out what was going on here, but if I'm along this line, it's pretty clear from the picture that the minimum is going to lie presumably either here or here, where it sort of cuts into the banana. But it turns out this was where the first optimization ended up saying it had found the optimum, which is clearly not the right answer. And then when I did it, for some reason I think I don't. This is not like a recommended solution to this, but I just removed the analytic gradient function and just retried it. And when I went ahead and did that, it seems like it found something that was much more plausibly the minimum here at point number 2 here. So I don't know exactly what's going on here, and I didn't end up delving further into it, but that was just to give sort of an illustration of exploring the use of this function in a few different ways. Okay, any questions or comments?
So do we need to specify the iterations?
No, but usually like with optim or with constrained, or in this case with constrained optim, it's a good idea to see, well certainly you'd want to check whether it seems to be indicating that it's converged, which in this case presumably 0 means convergence because it does in the optim function 0 means that it thinks it has converged. So let's see if it indicates here. Actually, it doesn't seem to say here what 0 means. However, since it's actually just passing stuff on through to optim, that's probably a pretty good indication that the 0 means it thinks it's converged, even though in this case it actually hasn't converged. Wait, so what was your question?
Oh, like do we need to specify the number of iterations?
Oh, the number of iterations, right. So
the of 1 doesn't seem to
yeah, so often you'll be able to control the maximum number of iterations. So for example, if there's a control argument for optim, that if you pass a control argument to constrained optim, that will just get passed along to optim. So that would control the maximum number of iterations within each call to optim. Of course, this has a nested loop because it's also got that barrier function where it's doing that approximation. And I don't know, when it says outer iterations, it says 100. And I presume that's the maximum number of outer iterations rather than the actual number of, because here it says it only did 7 iterations. So I think that must be the maximum number of iterations. So one thing that could happen is you might find it converges slowly. It reaches the maximum number of iterations either in the inner loop or in the outer loop. And at that point, if you might want to just allow it to use more iterations in hopes that even if it's converging slowly, that it still is converging. So those would be the sorts of things you'd want to look at. Other questions? Okay, so let's switch over to the integration and differentiation unit. Okay, so the idea here is just to explore fairly briefly what is going to happen on a computer if you try and numerically estimate a derivative or numerically estimate an integral. And so the places that this would come up, well, derivatives, obviously we've already seen that when we do a lot of these optimization methods, we've seen that we need to calculate derivatives. And in many cases, we haven't been passing in an actual explicit derivative function. So R behind the scenes is numerically getting an estimate of the derivative. And I thought it would be worthwhile looking at some of the details of how that would get done on a computer and what are some of the implications of the fact that we can't calculate precisely on a computer. And then in terms of integrals, I guess this would come up in sort of varied circumstances. But one case where this would come up statistically is in some cases you might have, say, a marginal likelihood where suppose I had a generalized linear mixed model. So I'm going to assume that I have, say, a Poisson model, and let's see, how do I want to do this? Xi. Okay, so without this piece here, this would just be a standard Poisson regression. I'm just regressing on covariates, the x covariates, except I need a link function in here, obviously, because the Poisson mean has to be non-negative. In this case, this is adding in a random effect into the model. So you might have this model where you then have BI, say, distributed normal, 0, and some variance. So this is one way to introduce basically correlation between units in a model. It's also a way to introduce over dispersion. So this sort of model comes up in a lot of different contexts. But one of the ways that people end up wanting to estimate the betas in this model is actually to integrate over the b's. And so one way that you could write this model is you could say, well, the likelihood would be the integral of f of yi given beta and b times this distribution. So I'll call this normal distribution pi of bi. So if I were able to do an integral like this, then I'd basically integrate over the random effects and just produce a likelihood that was just a function of the betas. And in high enough, if you have more than one bi, which in general situations you would end up having, this would be a multivariate integral, and we'll see that it can be hard to do multivariate integrals numerically on a computer. But the idea is the reason that you might want to do an integration of some sort or another is that you might have a situation like this where you're basically trying to integrate over a term in a log likelihood, for example. Or as we've seen with the EM situation, there was an interest there in integrating over missing data. So this sort of thing comes up in a few different ways. Okay, so if you're willing to take my word for it, based on that fairly brief description, that we are interested in doing numerical derivatives and we're interested in doing numerical integrals, let's talk a little bit about how that would actually get done on a computer. Okay, so the first thing to think about is, let's first look at derivatives and think about how we might approximate that on a computer. So if I have some f of x, then sort of the most naive thing you could do, but one that would actually work fairly well, is say, okay, here's x. I want to get the derivative of this. So I want to get the gradient of this function at x. So maybe what I can do is I can take x plus some small number h. I'll go from x. I'll go over to x plus h. I'll find that point there. I'll draw the secant between those 2 points. And that secant will, if h is close enough and if the function is not too wiggly, that secant, the gradient of that secant will approximate the actual gradient of the function. So if I did that like this, I would have my estimate of the gradient would just be the difference between f at x plus h and f at x divided by the size of the step that I took in moving away from x. Okay, and you might say, well, that seems a little bit weird because you've got this sort of asymmetric situation where you're from x, you're sort of moving away only in one direction. And maybe a smarter thing would be to go in the plus h direction and the minus h direction. And in that case, I would then be drawing a secant from this point to this point. And because of the symmetry here, maybe that would give me a better estimate of what this derivative is than if I just go in one direction and use x and x plus h. So one downside to this is if I had, for example, if I had already calculated f at x, this would only require one more calculation of the function f at x plus h, whereas this would require me to evaluate f twice. So depending on exactly what calculation this was all wrapped up in, this might require twice as many calculations as this one would. So it sort of all depends on the trade-off between the accuracy and the number of and the cost of the computation. But these are two different discrete estimates of the derivative. So the other thing I want to talk about, and we'll see this as an example in a second, is if we look at this and think back to Unit 7, was it, when we were thinking about computer arithmetic, we can think about what the drawback of trying to do this calculation is from the perspective of what if we let h get smaller and smaller? Because of course, as h gets smaller and smaller, in the limit, as h gets smaller and smaller, this is the actual derivative, right? That's the mathematical definition of the derivative. So you can imagine that as I let h get smaller and smaller, I should be getting a better and better estimate of what this derivative is, just because we're now getting closer and closer to the actual limit that we're trying to evaluate. So the question then is, well, what would prevent us from just making h, smaller and smaller and smaller, and doing this, sort of at a sort of infinitesimally small change in terms of going from an infinitesimally small value of h. Okay, so the first thing I want to sort of point your attention to as we think about that is, suppose that I have x, and then I want to take some very, very small h and add it to x. And figure out what x plus h is. What happens numerically as I let h get smaller and smaller from what we talked about in Unit 7?
X stops changing.
Oh, well, okay, so I've got x, and then I try and calculate x plus h, and what happens?
Nothing happens.
Okay, you get the same. You mean you get the same thing, right? So there's machine epsilon coming into play. If h gets if x were around 1 and h gets to be smaller than machine epsilon, I'm going to add something smaller than machine epsilon to 1, and I'm just going to get 1 back. So I would do, so then I just get the subtraction, and that'd be 0, and that's obviously a bogus answer. Suppose h is not quite that small, but is still small, and now I find out what f at x plus h is and what f at x is, and I try and subtract them. What could go wrong numerically from that perspective?
There's a variation of x around f of x plus h is very slow around x.
Mm-hmm.
You can get actually a number of difference that would be lower than machine epsilon.
Yeah. So the question is, well, what happens to the accuracy as we do this subtraction? And it's, I guess I wouldn't say it's so much that we get something smaller than machine epsilon. It's that we get something that we remember catastrophic cancellation, that if we have two numbers that are basically the same magnitude, and they're very, very similar, or they're very similar magnitude, as we do a subtraction, many of those digits that are left after we do the subtraction might be digits that are basically in the garbage positions of doing the calculation. So if this f at x plus h were, say, could even be 0.000435792 and then I subtract off something that's 0.004357923, and then I have some other digits here and some other digits here. Well, all of these digits here that cancel are going to, like we saw in Unit 7, are basically going to be wasted after having done the subtraction. And I'm only going to have, in this case, I would have lost six digits of accuracy. But you can imagine as I sort of make this a more extreme case, I could lose more and more digits of accuracy. So that could certainly come into play as well. Okay, so let's see, questions or comments about that? So this is a good example of where what we'd like to do mathematically differs from what we're actually able to do practically and carry out on a computer. Mathematically, we'd like to let h get really, really small. On a computer, as we let h get smaller and smaller, both of these two issues that we just discussed could come into play. Okay, so what I'd like to do here is I'll just show you an actual numerical example just to actually see that in action. Before I do that, I'll just say if you wanted to calculate second derivatives, and this would obviously be of interest because we were talking about Hessians all throughout the whole discussion of optimization. So we were talking about calculating second derivatives, potentially doing it in a numerical fashion like this. Well, you can just do the same thing that we did on the previous page, but do it to f prime itself. Okay, so I could estimate f prime at x plus h, estimate f prime at x, do this subtraction, divide by h. If I actually write this out and sort of work through what that means, well, I can write this out actually as a function of just evaluating f itself. It involves evaluating f itself at 3 different points, x plus 2h, x plus h, and x. And that would be sort of the analog of doing x plus h and x. And if I wanted the analog of doing x minus h and x plus h for a more accurate estimate, then the central difference estimate for f double prime at x is to calculate it like this. So you can see here I went plus 2h, here I just went plus h and minus h. And then if you were thinking about a multivariate x where I wanted to differentiate, say, with respect partial derivative with respect to, say, x1 and x2, you can think about taking derivatives in particular directions, and that's what I've written out down here, where with this vector ei just represents the direction in which you want to calculate the derivative. Okay, so this question about numerical issues, so this basically sort of says so much of what we were just talking about a second ago. So here's the example I thought I would walk through. So this is the log of the idea is to estimate the first and second derivatives of the log of the gamma function. So this is the function that, if you saw it written out, people would write it out like this. You can relate factorials to the gamma function. For those of you who remember that about the gamma function. It's not actually all that important what the gamma function is here, except from the following perspective, which is that if you actually work with the gamma function, you can actually write out what the first derivative function is and what the second derivative function is analytically. And there are functions in R called the digamma function and the trigamma function that will actually evaluate that first and second derivative. So the idea is we actually have a pretty accurate estimate of the first derivative of the log gamma function, in this case at the point x equals 1/2. We have a pretty accurate estimate of that using the digamma function and the trigamma function, but we're going to pretend for the moment that we don't actually know that, and we're going to try and use numerical methods to estimate the derivative by doing the whole x plus h and that whole business. So if we do that, I'm going to do a discrete difference approximation, but I'm going to do it for lots of different values of h. So I'm going to try h equals 0.1, h equals 0.01, h equals 0.001, all the way down to h equals 1 times 10 to the minus 15. And what we'll do is we'll see where the numerical limitations come into play in terms of the calculation breaking down. Okay, so here's me calculating the function at x plus h, the function at x minus h, the function at x plus 2h and x minus 2h, and then trying to calculate numerically these first and second derivative estimates. And then once I've gone ahead and do that, I can then see for a given value of h, what is my estimate of the derivative using the forward difference and the central difference, and for the second derivatives, the forward difference and the central differences for the second derivatives. So I'm basically just saying, okay, for the first derivative, how accurate is this one and this one, the forward difference and the central difference, and for the second derivative, how accurate is the forward and central versions for the second derivative for different values of h. So if we go ahead and try that out, okay, so here's me setting up a whole bunch of different values of h, and then writing out the results. And of course, since I'm in our studio, I'm going to have problems with the size of the screen. Okay, so the correct answers up to 6 or 8 digits are, for the first derivative, minus 1.96, I have it, 351003. And for the second derivative, 4.934, 8022. Okay, and here are the different values of h from 0.1, 0.01, 0.001, etc., etc. And we can look and see where we start to get pretty accurate results. So 1.9635, 1.9635. So I'm doing pretty well here already by, say, h equals 1 times 10 to the minus 5. You can see I'm more accurate actually with the forward difference, with the central difference than I am with the forward difference, not surprisingly given what I had said before. And you see, for example, for the central difference, I get to basically 8 digits of accuracy here after h is 0.1 times 10 to the minus 5, and that persists up to h is 1 times 10 to the minus 8. But then as I start to get smaller and smaller h, you can see that things start to break down. and I'm actually losing digits of accuracy as h gets smaller and smaller here. So in this case, the best I can do is somewhere between 1 times 10 to the minus 5 and 1 times 10 to the minus 8. We could look at further digits to see which of these is the most accurate, but this illustrates that things get worse as I try and, if I try and think, oh, if I'm just trying to act as a mathematician, I want to let h get really small, but things get worse and worse actually at some point as h gets smaller. And actually as h goes down to 10 to the minus 14 and 15, you can see that I'm actually only accurate up to say about 2 or 3 digits here. Okay, so I've actually lost accuracy.
Is that because of machine epsilon?
And that's because of all the things that we were talking about in terms of the catastrophic cancellation. In this case, it's probably not having to do with the x plus h and the x being the same, because if that were the case, we'd just get 0 back. But it should have to do with catastrophic cancellation. And if we look at the second derivatives, so here's the forward difference approach to the second derivative, here's the central difference approach to the second derivative. We're looking for 4.9348. 4.9348. So you can see we get to 9348022, So we get to about 6 or 7 digits of accuracy with h being 1 times 10 to the minus 4 with the central difference approach. And then actually after that things get worse as I let h get bigger, let h get smaller and smaller. And you can see once we get down to here, I get some zeros, which might be because of machine epsilon and the x plus h not being any different than x. And even here, I've got all sorts of crazy things going on in terms of actually get an answer that's totally ludicrous. And basically the same thing presumably happens here with the forward difference. Although I actually never get to even four decimal places of accuracy here. The most I can get is 934. This is the best, and that's only accurate up to about 4 decimal places, 3 or 4 decimal places. And again, all things go haywire here. So the higher order derivatives, the worse this is, and more generally, you want h to be somewhat small, but you don't want it to be too small, or these numerical issues will come into play. Okay, any questions about that? Comments? So if you actually look at the documentation for some of the numerical derivative functions in R and other packages, what you'll see is they'll say in the arguments what value, what size, magnitude of h is going to get used in doing the numerical derivative. And sort of a rule of thumb is that for first derivatives to make h proportional to, well, it's sort of, I guess the rules of thumb are a bit squishy, but to think about having h be proportional either to the square root of machine epsilon or the cube root of machine epsilon. So either something like 1 times 10 to the minus 8 or something like 1 times 10 to the minus 5. And as we just saw in the example, the values around there was where we were doing pretty well in terms of this trade-off of having a small h, but not so small that we got into the realm where numerical inaccuracy came into play. Okay, and if you were trying to, instead, this was obviously me just coding up the discrete difference estimate of a derivative myself. There is a function in R that will do it called numeric deriv in the num_deriv package. And so you could just, you can give it you can give it an R expression. Remember, you have to use this quote function so that R doesn't evaluate the function but treats it as an R expression. And then you can say, oh, differentiate with respect to x. And then it will then go ahead and give you the derivative of interest, an estimate of the derivative of interest. And this is going on behind the scenes if you call optim without providing a derivative function. It has to do numerical derivatives, and so it's I don't know exactly if it's calling this numeric deriv function or a different implementation, but it's calling something like that. Okay, and then if you did want to do symbolic differentiation, so if you want to try and mathematically find the derivative, obviously you could do it by hand. You could try to do it by hand. That's going to be prone to you just making errors in writing out the derivatives, particularly as the functions get more complicated. R has some ability to calculate symbolic derivatives, so you can give it an expression. So, for example, if I wanted to find the derivative of the arctangent function with respect to x, I can call the deriv function, and that will then give me back an expression that when evaluated would calculate the analytic well, it would numerically calculate this analytically derived derivative. So that can be useful. Actually, if you recall, I used this in one of the examples in the optimization unit when I was interested in actually passing in a derivative function. Instead of doing the derivative by hand, I did it with a function like this and then coded up a function based on the results of having done something like this. If you really wanted to do sort of more complicated functions and have them done symbolically by the computer, you'd probably want to fall back on something like a Mathematica or a Maple, which are really developed in part to do this sort of symbolic manipulation. Okay, questions, comments? All right, so let's, and this is just a bit of an example of what the syntax would look like in Mathematica. Okay, so let's talk a little bit about integration and get started on that, and then we'll finish that up on Wednesday. Okay, so a few sort of high-level comments on doing numerical integration on a computer. So one is that methods for numerical integration are really well developed, so you would never want to code this up on your own. There's tons of software for doing integrals on a computer and implementing a variety of different methods. The other is that what really matters when you're choosing how to do an integral on a computer is what the dimension of the integral is that you're doing. So if you're doing a one-dimensional integral or maybe a two- or three-dimensional integral, there are a lot of good methods that you can use that go under the name of quadrature, which we'll see in the next few minutes. But as the dimensionality increases, so if you were doing a derivative that was, say, a function of 5, 6, 7, 8, 10, 20, 100 different variables, the accuracy of using these quadrature methods sort of fails catastrophically. And so if you were doing integrals in higher dimensions, you would want to use Monte Carlo integration, which we've actually already seen an example of in the simulation unit. So one way to think about that is to remember that what did we see when we were doing Monte Carlo integration in the unit, whatever it was, unit 12, I guess. We saw that if I wanted to calculate something like the expected value of h of x when x is drawn from some distribution density or distribution f, that, well, of course, that's just the integral of h of x, f of x dx. And then I can approximate this by drawing a whole bunch of values independently from the density f, and then just taking the average 1 over m of h of xi. Right, so that was our Monte Carlo estimator of this integral. So as long as I can write out the integral that I want to do in this form, and there's no reason that I couldn't say, suppose I wanted to do the integral of some g of x dx. There's no reason I can't introduce an f of x by multiplying and dividing, and then I've just got integral of g of x over f of x dx, where f is a density, and now I've got it in the form where I can use a Monte Carlo estimator. Okay, so an example of that would be, suppose that I, for some reason, wanted to integrate the sine function from 0 to pi, and then I couldn't do that in closed form because I had forgotten all of my high school or junior high school trigonometry. Or I guess that was calculus, but maybe I'd also forgotten my trigonometry as well. Well, in this case, I can get this in the form that looks like a function times a density by just saying, well, let me just use the uniform density from 0 to pi. And so in that case, I'm just going to multiply and divide by pi, because that's the value of the uniform density on an interval from 0 to pi. And now I've got this in the form that I'm going to take the expected value of this function with respect to x being drawn from the density f, which is this uniform density. Okay, so if I did, so I can go ahead and do that. And what I want to do is compare it to the Monte Carlo approach to doing it using one of these quadrature methods. So I haven't actually told you much about quadrature, but think back to doing the trapezoidal rule or Simpson's rule or those sort of things, that sort of thing, and we'll talk about those in a little bit. Those are all different types of quadrature that you could use. And in fact, the integrate function in R is doing a type of quadrature. So if I wanted to do this integral in R, I could say, okay, integrate the function f, which I've defined as the sine of x, between 0 and pi. And if I go ahead and do that, it says, well, that integral is 2, and it's able to get an estimate of the error in doing the integral. I think I forgot to look up exactly how it does that, so I can't tell you that off the top of my head. But I could also do this as a Monte Carlo integral. So this is just me writing this up as a Monte Carlo integral, sort of doing it in shorthand. I'm generating a whole bunch of values uniformly between 0 and pi, calculating the sine of that, and multiplying by pi. So this is me just implementing the Monte Carlo estimator that I mentioned before. And if I did this with, say, 1,000 different samples from this density, doing the Monte Carlo estimate, you can see I don't actually get a very accurate approximation. So assuming we believe what we got from quadrature from calling this integrate function, that 2 was correct, and obviously we could work it out by hand and see that that's actually correct. What we see is if we only use 1,000 draws from the density, I get an answer that's 2.06, which isn't all that close to being the right answer. And so okay, maybe I will increase it and take 10,000 draws. And now I get 2.01, so okay, things are getting better. I might try and say, okay, well, I'm going to do 1,000,000 now. And I can get a more and more accurate answer. Now I'm accurate up to about 3 decimal places, but now it's taking longer and longer. So now it's taken me about 1/10 of a second to do that calculation. And all I was doing was just calculating a one-dimensional integral. So it's basically a sort of yin and yang sort of thing here. If you have a low-dimensional integral, it's going to be much faster and more accurate to use quadrature. But if I were to try and do an analog to this same problem in, say, 10 dimensions, I'm going to be much better off using Monte Carlo integration than I am using quadrature techniques. And we'll see in more detail why that is next time. So let's see what I want to say next. So okay, so that was just working through the example. Okay, so any questions about the example before I start talking about some of these quadrature methods? Okay, so I'm not going to go into a huge amount of detail here. And what you'll see is basically some of these methods are the sorts of things that you've already seen when you were taking various math courses in high school. So a basic way of writing out numerical integration is to say, well, if I want to approximate f of x over the interval between a and b, let me split it up into a bunch of different regions and then get an estimate of that integral in each of those regions and just sum up those pieces. So just sort of the obvious sort of thing. Suppose I have some function that looks like this between a and b. If I choose basically a grid spacing h, so suppose I choose a grid spacing like this, well, my task, sorry, this was supposed to be equally spaced. Well, now my task reduces down to how do I approximate the integral of this curve over this small region, how do I do it over this region, and then add those pieces together. So just some notation that people use when they're doing this is they'll say, okay, let's write it out like this, and then I'm going to write out the little piecewise integral between x at I and x at I plus 1, so for any one of these little regions here. I'm going to write that out as a summation from j equals 0 to m of some coefficients here times evaluating the function at some places, some xij star values, where the xij star values are basically going to be values in. So if this were xi and this were xi plus 1, the idea is that sort of the generic algorithm is I'm going to choose these values that I'm going to denote as the xij stars. I'm going to evaluate the function at those places, and then somehow I'm going to have some coefficients that allow me to basically combine the information from these different points and estimate the integral. All right, so that, as I was saying, that may not have sounded all that clear, but I think it will be clear once we see a few examples. we're going to write this out. We're going to write out that sort of generic formula in terms of examples of integrals, forms of integrals that you've already seen from calculus. So the idea is what's called Newton-Cotes quadrature takes those intervals to be of equal length. So we're going to say the length of each interval is h, and we're going to get that just by taking the length of the total interval divided by the total number of points along here that we specify. And then within each interval, we're going to come up with a polynomial approximation to the function here. And once we have a polynomial approximation, then you could just analytically calculate what the integral is of that polynomial approximation to the function. So here's where just sort of standard kinds of results from calculus that you've already seen before come in. So we can think about using Riemann's rule to do this, we can think about using the trapezoidal rule to do this, and we can think about using Simpson's rule to do this. And so if we think about using Riemann's rule, well then of course what are we going to do? We're just going to basically evaluate the function at the left-hand point in the interval here. We're going to draw a straight line and we're going to say, okay, my approximation to the integral in this region is just the size of the block. So this is sort of a zero-order polynomial approximation to the actual function here. And so here are the coefficients that we're multiplying by the evaluation of the function. So you can see that this could just be written out in this form here where I have these aij's and xij stars, except in this case it's a very simple example of that because I just have a single evaluation and a single coefficient in front of that. Obviously that's not going to give us a particularly accurate estimate unless we let h get really small. And of course as h gets smaller and smaller, we would also start to run into numerical issues in doing numerical integration, just like we saw in doing numerical derivatives. And we'd have to do a lot of function evaluations as well. So of course the trapezoidal rule says, well, let's take the polynomial that approximates the actual function to just be a linear approximation. So okay, I'm going to evaluate f at xi and f at xi plus 1. I'm going to do a linear extrapolation, and then I'm going to figure out what the area of the trapezoid is. Okay. So if we think about how we write that out, well, here's a coefficient multiplied by evaluations of the function. So this also falls into that sort of generic formula that I showed you a second ago. And if you write out what Simpson's rule is, well, instead of using either a constant or a linear approximation to the function in the interval, you're using a quadratic approximation to the function. And if you just work through the details, what you'll see is that this amounts to taking this and multiplying by this linear combination of evaluating f at the endpoints of the interval and at the midpoints of the interval. And again, you can write that out as a set of coefficients times multiplied by a linear combination of coefficients multiplied by function evaluations. Okay, so as you increase the order of the approximation, you're going to get a more and more accurate estimate of the integral. And so usually people will write this out as being quantified as a function of h, which is the size of the intervals that we're looking at. And so if you work out some of the details of what these errors are, if you do the trapezoidal rule, the order scales as h squared, and of course h is small, so it's good to have h being raised to a power. And Simpson's rule scales as order of h to the fourth. So you get this sort of extra bang for your buck from having done the higher order approximations. Okay, so let's quit there. I'll say a little bit more about some other quadrature approaches next time. In particular, the integrate function in R actually uses something called Gaussian quadrature, which is somewhat different from this Newton-Cotes quadrature that I was just discussing. And maybe I guess we might see a little bit of an example. Oh, I guess the main thing I want to talk about next time before we finish up this unit is I'll give you some more information, some more of intuition as to why it is that doing quadrature scales really poorly, whereas doing Monte Carlo integration scales quite well.